Hi students, in this final video for online lecture 6, we are now going to talk about the electron configurations of our ions. So we are going to talk about two really kind of different ions throughout this section. Ions created by what we call the representative elements, those are the S and P blocks, and then eventually we'll talk about the transition metals. So if we go and look at our species here, you will see that if I have sodium, calcium, and aluminum, these are typically metals. These species like to lose electrons to form the cation, which is going to be the positively charged species that has the same noble gas notation of the previous noble gas. So as you see with sodium, I have neon 3s1. If I were to go and remove one electron, I would remove the 3s1 electron, reverting back to the neon electron configuration. If I go in calcium, you'll see that that was argon 4s2, and I can remove 2 electrons to form the calcium 2 plus cation. Finally, with aluminum, you can see that I have 3s2, 3p1, and if I lose those 3 electrons, I will revert back to neon as well. So now we are going to look at situations of whether it is easier for us to gain electrons or lose electrons. In the case of metals, especially those on the left side of the periodic table, it is better for us to lose electrons to go back and revert to the previous noble gas. So now let us go and look at the opposite case. Let's look at species that gain electrons. So here you will see that hydrogen is 1s1. But if I want hydrogen minus, or hydride as we'll call it, we are going to add an electron. You will see that this electron is added in the 1s orbital as well, and that will give us helium. For fluoride, one of the most reactive halogens out there, notice that I have 2p5 ending its electron configuration. If I were to add an electron and make fluoride F minus, you will notice that it will go to the noble gas that is immediately next to it. So the rule of thumb that we are going to have for species that gain electrons, our anions, is that atoms will gain electrons so that the anion has the noble gas outer electron configuration of that of the next noble gas. So if you look at oxygen, oxygen is 2p4. Well, how many electrons do I need to fill up the 2p subshell? Well, I need 2 of them. So now what we are going to see is that our oxygen would prefer to be O2 minus as an anion. Nitrogen, once again, has 3 open spots. This is a Huns compliant species with 2p3, each one needing a buddy. So in this case, we can add 3 electrons, creating the neon electron configuration, and this is how we get the nitride 3 minus anion. So let us go ahead and look at our representative elements to begin. For our column 1, these are historically +1 cations because they will revert back to the previous noble gas. For our 2A column, or our alkaline earth metals, notice that we can go and lose both electrons in that S subshell. So even though it is a full subshell, if we were to remove them, we are actually going to the shell previous, and that is how we gain stability. For our boron group, especially in the case of aluminum, gallium, and indium, these are going to be +3 because we are going to have an electron in the p orbital. So we are going to try and remove not only that electron, but the 2 electrons that show up in the s orbital of the same principal quantum number. If I look here at my halogens, these would prefer to be -1. It is easier to gain 1 electron to gain the noble gas stability instead of trying to lose 7 electrons. If I go to the oxygen group, you will notice that they are -2. And finally, we get to nitrogen, which is -3. Let's go ahead and discuss such things when it comes to carbon, silicon, germanium, tin, and lead. This group is stuck in the middle. Is it easier to gain 4? lose 4. Well, in the case of carbon, this actually brings out one of its most important properties, and we historically don't like to gain or lose any of those electrons. This is why carbon likes to share electrons, and we will see that once we start to build compounds. Silicon likes to share them a notch less. And finally, when we get to tin and lead, we actually like to form the +4 cation. So for tin and lead, it likes to be +4. Now, in the case of carbon, in some rare exceptions, we are able to give enough electrons and force them into our carbon, in which we can make this -4. So the reason why I don't highlight this as an entire group is that the periodic trends and typical properties of this group are widely diverse. Carbon would like to form carbide only in certain situations to form -4, but as we get down to our tin and lead, those very much like to be +4 and lose those electrons. So in our groups, we like to discuss this as a trend. Our +1 for our alkali metals, +2 for the alkaline earth metals, our -1 for our halogens, -2 for the oxygen group, and -3 for the nitrogen group. But for the most part, this is where that diversity is a little bit different. What does it mean to be isoelectronic? This means that you have the same number of electrons and hence the same ground state electron configuration. This means that species with different charges might have the same number of electrons, and thus we can call them isoelectronic. So let's look at sodium plus. As we saw in our previous example, it has the same electron configuration as neon. Aluminum at a 3+ cation also has that same electron configuration. If I look at fluoride, which is 1s2, 2s2, 2p6, which happens to be neon by gaining 1 electron, also has the same electron configuration. Our oxygen 2-, our nitride 3-. So the nice part about all of these are these are considered isoelectronic. Iso prefix normally means same, electronic meaning electrons. They have the same number of electrons. So even though they have a different number of protons identifying the element, if they have the same number of electrons and the same electron configuration, we can consider these isoelectronic. This is a nice definition for us to have. So now let us go look at the group that confuses many first-year students, and that is the transition metals as well as the rare earth metals. When we are forming a cation from a transition metal, the electrons are always removed from the s orbital first and then the d orbitals. So what does this mean? Let's look at iron. The ground state electron configuration of iron for the neutral atom is argon, 4s2, 3d6. So that means that if I want the 2+ cation, I am going to remove the s electrons. Now, this is just a temporary notation. You will never put 4s0. The reason why we do this, if it is an empty orbital, we've never put it. So now the correct notation in writing this would be considered argon 3d6. Is that the only thing I can do? Well, now look what happens if I have my iron 3+. I will remove the 2s electrons first, and then I will take 1 electron away from the 3d subshell. This now gives us argon 3d5. So what is so important and so good about our iron 3+? Well, now this is Hund's compliant. Because we have 5d electrons in our 3d subshell, this means that this is a half-filled subshell and is incredibly stable. So what other examples can we do? Well, let's go look at manganese. Notice for manganese, I have argon 4s2, 3d5. So if I would like to form manganese 2+, notice that I will go and remove the 4s electrons first, and I am left with argon 3d5 which is also Hund's compliant, and this is why our manganese 2+ is incredibly stable. Another important thing is, let's talk about the rule of thumb. The rule of thumb is a nice way to remember exactly what you're doing with the transition metals. This rule of thumb states, add electrons using the atomic number trend in the periodic table. So that means if we were wanting to add electrons to such things as our halogens, you just add it in the same order. But if we are removing, you are going to want to remove from the highest principal quantum number first. So in the case of manganese, that is why we are going to go after the 4s orbital first before going to the 3ds. If we start having f electrons in the case of the rare earth elements, you might have to go after some of those, but historically they have a lower principal quantum number, so that might mean that they will stay intact. You want to add in order, but you want to remove by your highest principal quantum number. This means that you want to write the ground state electron configuration and then remove from that configuration. Let's go ahead and try a couple of examples. So let us go and look at our sulfur. What is the correct electron configuration for my sulfide ion? We'll notice that it has 2 extra electrons because it is 2-. So as we're looking at this example, we know that we would have 1s2, 2s2, 2p6, 3s2, and finally, our ground state would be 3p4. But now because I have the 2-, I need to add 2 more electrons. Where I'm going to add that to is my 3p subshell. So if I add 2 more electrons to this case, I am going to end up with 3p6, and this will give me the correct answer of letter E. So once again, as we're adding electrons, we want to add them in the typical order that we have seen with the periodic table. So now let us go and look at the electron configuration for zinc. Well, what could this possibly be? As you see here, we are going to have the use of our noble gas notation. So for our zinc neutral atom, that is going to be argon, 4s2, 3d10. But now you'll notice that I have the 2+ cation. In this case, we need to go and remove 2 electrons. We are not going to remove 2 electrons from our recently added. We need to go and remove 2 electrons from our highest principal quantum number. So for this to be done, I will have zinc 2+ being equal to my argon electron configuration, but now I will remove those 4s2 electrons, and I will be left with 3d10 as my electron configuration, which you will see here is going to be answer C. So in this video, you saw the importance of adding electrons to form anions, as well as removing electrons to form cations of either the representative elements, which are fairly easy and go back to the previous noble gas. But in the case of the transition metals and the rare earth metals, they are going to remove from the highest principal quantum number first. Make sure that you know the difference when doing this procedure. Have a great day.